As we all know, projectors are the hardest technical problem in the world. So in comparison, this is going to be a very easy talk, so everything's fine. So this talk is about shared state in purely functional programming, and specifically when a state moment won't do. So I'm going to try and explain what all these terms mean, and then can I tell you not only how this is done, but also why you should do it this way. So first of all, who am I? My name is Fabio. I'm a principal engineer here at OverEnergy, and an open source author of System of Omega. I'm a co-maintainer of FS2 and Cat Effect and a bunch of other libraries in the purely functional Scala ecosystem. And let's get straight into it. So purely functional programming. What is this thing? There's a lot of misconception around about not doing side effects, not writing to disk. So how do you even do this stuff? So as it turns out, most of the problems are with an incorrect definition. So the whole of PureFE is based around this property called referential transparency, which means you can always replace an expression for its bound value without changing the result. Now this might look a pretty hard thing, but actually something we're all already familiar with from basic math at school. If I tell you that x plus 2 equals 3, and then I tell you that x is 4, what you do, you just replace 4 whenever you see x, and then reduce. So all that this is saying is that you want to be able to do the same thing with your programs, and then we'll see why you might want this property to hold. So let's look at some code. Let's apply this substitution and see what happens. So the first thing I have there, I just have a string that I'm reversing, and then I'm appending the string to itself, and the result obviously is hole hole. And to see if referential transparency holds, I'm just going to do what I would do with math, right? I'm going to replace x, whatever I see x, in the bottom definition, and we're going to see what happens. So same thing, hello reverse plus hello reverse. As you can see that this is the same result, hole hole. So this is pure, it's referentially transparent, because we did the substitution and everything worked the same. But now what if I have this side effectful thing, started in .readInt, and I read into an int, and then I sum the two ints. So let's say I input 2, and then I sum it to itself, then it's going to be 4. Okay, so now let's do the same substitution as before, because as we said, we want to do this substitution to see if our code is purely functional. And obviously it's different, because now I'm going to do 2 started ints, and I'm going to read 2 numbers. So the behavior has changed in between. When I replace the thing in the value, the behavior has changed. So this is not pure. It does not hold. The property does not hold. And then if you've seen future, you might think that it's different, but actually it's the same. So the mapend there is from cats. It's just they combine 2 things together with a function. And then I have the val read, which is a future, so it reads like asynchronously. But then when I go and replace it, the same thing happens. This is like a side effectful thing. It's going to start 2 things. So this is also not pure. So by now, for most people, they associate, well, if I only have additions and stuff like that, that's pure. But if at the moment I start having standard input and files, then it becomes impure. It's actually not true. It's just a matter of whether that property is respected or not. And in fact, if we use cat effect IO, we have a program. So the way you look at the IO is like a little program that is describing an action, and the action is read from a file. And when you do read, you're just saying, well, I have 2 programs, I'm going to run these 2 programs and combine the result. And so the main difference here, so with future, when you do this, something has already started. And so the property is broken, whereas here, nothing is started. Nothing happens when I do var read. It's just a program that doesn't execute anything yet. And then I can compose programs together to build this massive program, which is the whole thing. And then at the end of the day, at the end of the world, I'm going to say, well, run the resulting program. And as a consequence of that, the substitution holds. Because it's just a program, I can just replace the definition of the program whenever I see the name, and the result doesn't change. And this is pure. And it's pure by definition, because we have defined purity as this property, referential transparency. And by the way, some people then say, well, how do you do the opposite behavior where you read once? Well, it's just simple. You say read, map, and then you x plus x. So again, you have a program. If you want to run it once, you just mention it once. So the mindset shifts from doing actions to composing programs. And so as a recap, side effects are things that break referential transparency. So that's the definition, nothing more than that. So I/O state and things like that traditionally are side effects because they break referential transparency, but they don't have to be. If you do them in a referentially transparent manner, then they're not, then they're pure. And why would you care? So there's a whole other talk just on this, but just to give you kind of an idea, because of referential transparency, I can always apply local reasoning. No matter how complicated the program is, I can always replace things until I have an expression that I can reason about in isolation. And once you have local reasoning, all sorts of awesome things happen. For example, two nice properties that we have is compositionality and composability. So compositionality is the ability to take a complex piece of code, understanding the individual parts of it, and then understanding the complex behavior by putting together the two parts I've understood in isolation. And think about this. When I understand something in isolation, I take a piece, analyze it, and then I'm going to replace that piece into its definition to see how it works together. Because I know that the behavior is not going to change, I can do this piece by piece. However, if when you replace things, some things happen, then you can no longer reason in isolation, because there are some effects that are isolated and some that are, kind of the interaction between these different things. So we're going to talk about a specific facet of this property, just with respect to sharing state, but actually it applies across the spectrum. Lack of referential transparency is always lack of compositionality, because you can no longer understand things in isolation without changing the behavior of your program. And also, referential transparency is also known as purity. So I actually don't really like the name purity, because you get this sort of moral quality between the pure code and the impure sinful ones. But actually, that's it. There's nothing more than that. It's a syntactical property which gives you certain semantical properties that you then care about. Okay, so sharing state. First of all, state is actually a very overloaded word. There are several things that we all talk about by saying state, but they're actually very different. First of all, there's local state. And by local state, I mean something that is just in the body of a function as a small optimization, but cannot leak out. So the function itself is referentially transparent, but inside the body is not. So a typical example, you have this map function on vector, which is called as an immutable data type. You can just implement it by pattern matching. But let's say for an optimization, I want to do it with a variable, a mutable var there, and an array buffer, kind of like a builder. So this inside the function, we are breaking referential transparency, but outside we're not. It's just takes a vector, returns another vector. So local state is actually off topic for this talk. I don't care about this. This is fine. Do it however you like. It's not really affecting the architecture of your program and your ability to reason at large. What I care about is when you want to share this state. So you have things that you want to share between different parts of the program. That's where most of the complexity hides, not in this little things. And yeah, from the outside, this function is referentially transparent. I can replace every call to, if I put map into a variable, I can replace every occurrence of the variable with map, and nothing's going to change. Okay, so state. If you've had any experience with functional programming, the typical answer when they ask you, how do you do state, is like, the state moment. So, or the state data type, to be more precise. So what I'm going to do, I'm going to explain what it is. It's actually fairly simple. Give you an example of why it's nice, and then tell you why actually, in most of the cases in a server-side code base, you cannot use this. It's useless. Okay, so we're going to talk about its limitations. Okay, so state is a data type, just like a list or an option or whatever. It has two type parameters, S and A, where S represents some sort of state, like an integer, and A represents the final result. And the semantics of this data type is that it describes modifications to an S, which then results to an A. So you imagine you have an S, you can apply a series of modifications, and at the end of this series of modification, you're going to have a final result, which is A. And S is an immutable data type. So what this thing is describing is the process of copying a data type, making some changes over several transformations. And then once you've described how all these transformations can be done, the way you run this state is just by passing the initial state. So I'm describing how this state needs to evolve, and then when I'm done describing, I'm done composing, I want to actually do it, I just pass the initial value for the state, and all the transformations are applied. And then it's very composable. There's a lot of kind of APIs that this thing respects. So these are fancy names, but it's just ways of building bigger programs from smaller programs. So applicative, we actually already seen that map-n thing that combined two computation into one with a function. So let's see how it's implemented. I only want you to look at the first line for now. So we're saying that state represents a series of modifications on an immutable data type. And then we're going to return a result. So the way we can represent this is just with a function that takes the initial state, and then it's going to return a result and a new state. And this function represents the entirety of what you want to do with state. So all these other things are just giving you a nicer API to compose these functions together in a way that is nicely from a semantic point of view. So imagine we start with an initial state, we build some stuff, and then we need to run it. As I've said before, running takes an initial state, and I have this function that represents all the transformation. So all I have to do is pass the initial state into the function, and then get the result out of it. So that's how you run it at the end of the day. However, we don't want to just like create one and run one. We want to compose these things together. And the primarily way is with this function called flatmap. And what flatmap is saying is this. Imagine you have a program, a state program, that modifies the state, describes modification of the state, and returns an A. And then I have a way of saying, depending on which A I return, I can produce another program. I want to get the resulting program that sequences these two together. This can sound complicated, but it's actually just stupid function composition. I need to return a new state, so I call the state constructor. State constructor needs a function, so I'm going to pass a function, which is from S to whatever. And I already have something, which is this, the current state. So I just call modify with this state. And what it's going to return is going to return a partial result and the next state. And then, if I pass result into F, so result is an A, I pass it into F, I get the new state. And then I just pass next state in. So you don't need to understand all the details of the code, but just what's happening is that you're threading these new copies in this chain of function composition. So that's it. So this is how you run a state, and then how you compose state together. But how do you create your initial mini-state programs? So it's a common pattern. You're going to have some primitives, which are your basic programs, some ways of, and these are the ones that we're going to talk about in a second, some ways of assembling these primitives into bigger and bigger programs, and that's flatmap. And then once you're done with this assembly, you run the whole thing. So the first thing is this pure, and pure is just saying I want to return a result without doing anything to the state. And this is exactly what the function describes. It takes a state, returns the result, which you need to pass in, and then returns the new state unchanged. So I'm not doing anything to the state I'm passed in. And then get is just saying, well, to get something from a state, it means to return a state computation that returns the current state. So I take the state, I don't touch the new state because I'm just a get, and then the result is just the state itself because I want to return it. And then finally, to set it, I'm going to ignore the previous state and set the new state to what I'm being passed in. So all I'm saying is that whatever you had before, I'm going to discard it and pass the new state to the rest of the chain of transformations. And this is kind of the same as mutation, basically. What mutation does is that at some point, I'm going to ignore the previous value of something and continue with the new one. And this is exactly the same thing. Anyway, no need to look into the code in detail, just the idea of describing these transformations. Okay, so an example. Actually, a typical example of this sort of transformation is a video game run loop, where you have a bunch of commands and something happens, and then you kind of loop around. So we have a very, very simple example here, which we're going to talk through. It's a very simple thing where you have you can basically damage or heal a character, and there are commands arriving that tell you either you damage it or you heal it, and you want to kind of modify the state of the character to respect these commands. So the way I do this is a simple data type. So a command can either be a damage, and it contains an integer, which is the amount of health you want to subtract, or it can be a heal, which is another integer, and contains the amount of health that you want to add to your character's life. And then I actually want to use the fact that state is composable to build a composite combinator. So a common thing that we want to do is take the previous state and update it. And because state is composable, so if you haven't seen this before, this is just a syntactic of a flat map. So what it's doing is calling state get flat map, and then keeps doing flat maps. And I'm going to say, well, what is it to update? It means that I want to have the program that gets, and then I'm going to do flat map on it, and I'm going to have the result, and then I'm going to apply f to the result, so it's going to change it, and then I'm going to set to the new state. And remember, what this is doing is not actually changing anything. It's just describing how this needs to be transformed. And bear in mind, this is again compositional and composable because I didn't do it from scratch. I didn't have to write the modify function. I just composed existing things, in this case just primitives, get and set. And then this health command is going to take one of the commands, which is going to be either a damage or a heal, and then return a computation in state that modifies an int, this is our health, and then returns unit. I just want to do this and don't return any result. So I'm going to do a pattern match on the command. This is the same thing as a switch, pretty much. It's going to say, well, it's either going to be a damage or a heal, and then I'm going to return the program. So if it's a damage, the program I want to return is this update thing by subtracting the amount of health. And if it's a heal, I'm going to do the same update, but adding the int. And then I want to do something else. I want to say, well, how do I report this final state? Again, it's a program that gets the current state and then map, so transform the result with the function from A to B, and just put it into a string. And those are all the primitives I need. So again, I'm building like slightly bigger programs from the small ones I started with. And then I have this list of commands. Imagine these are user inputs, damage of 1, damage of 5, and then heal of 2. And this is all coming from cats, and again, no need to understand all the details, but what this traverse is doing is basically walking over the list and applying any transformation as with the state data type to all the things in the list. So in this case, it's gonna, and the transformation we're gonna first do health, so it's gonna change the state, and then we're gonna compose it with report, which is gonna take the current state and transform it into a string. So again, I'm actually composing, I didn't build this monolithically, I'm actually composing smaller programs to get to the bigger program I want to have. And each of these things you can understand in isolation. I can replace health with this, I can replace report with this definition and understand exactly what's going on. And then I'm done, and then I want to run it with an initial state, which is the initial health. In this case, I'm going to say the initial health is 10. And this is the result. It's going to say, well, the current health is 9, because I decreased, and then it's 4, because I keep decreasing, and then it goes back to 6. So what are the nice things about this? So all is pure. You can do the replacement, and at the end of the day, it's just going to transform into function composition on immutable data types. So there's nothing that breaks referential transparency there. Second is compositional. This is the point I made several times. I'm just building bigger programs. And finally, it's testable. So let's say I want to try with a different initial state, like something weird, like 0. Or for example, I want to say, well, if I want to test it when the character starts at 45, how do you do it? Well, you just pass a different initial thing there, because what you want to test is just the transformation. And compare with real mutable state, you have to kind of set up mocks to make things into the initial state that you wanna test. So this looks awesome. So then why is it not cool for what we need to do? As it turns out, if you have a function and you compose it with another function, this is literally the most sequential thing you can possibly do. You take a result and you pass it to the next thing. So it's literally a pipeline. However, at least in server-side apps, there are other kind of scenarios where this makes sense. But in server-side apps, most state is concurrent. Think about a cache where you have evictions, things put in the cache and things getting in the cache, and it's not sequential. Or all sorts of user repositories, which again are like you might get from different threads or fibers or whatever. And also, state can only deal with immutable data types because it's just staying copy. But some things are inherently already mutable. Like if you get a JDBC connection from a Java library, that's already mutable. You cannot make it non-mutable. So we cannot use state. But can we keep referential transparency? Because at the end of the day, the reason state is nice is because I can assemble things, and the reason I can assemble things is because of referential transparency, of this property of replacing and substituting. So, spoiler alert, yes, we can. And you already actually seen this, the magic type that can do it. And that's IO from Cat Effect. So, same thing, it's a data type. I'm not going to talk about its implementation. I have another talk on how this works internally. But just the semantics. So the semantics that an IO array is something that will produce one value, or fail, or never terminate. These are the three things that it can do. And it's referentially transparent. I showed you at the start with that real line. And that means that it's pure. So common myth in functional programming, you have the pure side and the impure bit, which is IO. No, IO is 100% pure. So there's no tricks there. It's just that property, and the property is respected. And can suspend any side effect. So you just put a chunk of side effect in code, and it's going to suspend it. So it's not evaluated until the whole IO is being composed. And again, this has got many algebras. It's actually got even more algebras than just state, because we have an algebra, so an API for concurrency, for example, with lightweight threading that we implemented, or an algebra to suspend side effects, or an algebra for errors. So it's very, very rich in its compositional qualities. And the key idea is that if you want to do concurrent share state, it happens in IO. Or actually, you can actually abstract over this as well. So this is just for people who are already seeing Cat Effect, but we have actually APIs that describe all the different aspects of what IO can do. So you can actually say, well, I don't want to specify IO, I want to just say something that at least as capable as some of the things that IO can do. But this is not too important. We're going to kind of skip over this bit. Okay, so how do you design things when you have to deal with mutable data? So you can either wrap it directly with IO, I'm going to show you how to do it, or you can use Cat Effect primitives with immutable data. So as it turns out, for many, many things, a small amount of primitives can help you build a lot of things, and we've already put them in Cat Effect. But sometimes you're dealing with something that you cannot represent with those, like JDBC, and then you can wrap it directly. And general advice is use the primitives when you can, and only wrap directly when you must, because they're already like nicely done for you. So the thing is, like, I kind of want to show you both. So both how you wrap it directly and how you use the primitives. So the way I'm going to do it, I'm going to show you how the primitive itself is implemented. Because the primitive is wrapping directly, obviously. And then when you use the primitive, you don't have to do direct wrapping yourself. And to wrap, there is a very, very simple recipe. It's a dumb recipe. You don't have to apply any reasoning. Access, modification, and creation of mutable state, they all have to be wrapped in IO. It's as simple as that. So most people understand very easily why access and modification need to be wrapped. We kind of talked about it, but they get confused with creation. But if you don't put creation in IO, then you're going to get the same sharing that you have with future, where like when you refer to it twice, it's referring to the same thing, whereas we wanted to keep that substitution property. Okay, so let's enter the primitive. This is a ref. It's short for reference. It's actually, for those of you who know, is a thin wrapper over atomic reference in Java concurrent. So it's a purely functional, concurrent, lock-free mutable reference. We're not going to go too much into the why it's lock-free and all of that. But it's a purely functional mutable reference, essentially. And this is its API. So this F here, just imagine it's IO. So get is going to return an IO array for any A, and set is going to take an A and return an IO unit. And then you have these interesting functions, update and modify. I'm not going to go too much into why they're there, But just notice that update is not the same thing. It's not the same thing as get and then set, because obviously now we're talking about a concurrent capable data structure. If you do get and then set, you're going to get race conditions with other things. But that's not the important bit in this talk, at least. I have, again, other talks for that. Is this create? So because ref is wrapped into mutable state, the creation is wrapped in I/O, and so you get this shape, which is typical of f of ref of f and a. So this thing, if you start doing some purely functional programming in Scala, you're going to see it all over the place. So just get used to this pattern. And let's see how this is implemented. And again, it's just following the same recipe I gave you. So it's just a class. I have this atomic reference, which is private. I don't want people messing up with their state, because otherwise they can break referential transparency. And then every method is just wrapped in I/O, so that the side effect is suspended and doesn't happen as soon as you refer to that thing. So this is how update works. For those of you who are curious, I don't have time to go into the detail, but if you know sort of a bit of lock-free concurrency, it's just a cast loop over an atomic reference. So it's very simple. Gets a copy, tries to set the copy, and if there was a conflict, it retries. And this is non-blocking, so it doesn't block a thread, so it's way faster than a mutex or a monitor or whatever blocking primitive you wanna use. And then on create, it's the same thing, but I need to wrap it in I/O. It's for the same principle. I don't want that atomic reference to be shared freely. I want it to be shared only when I decide to do so via substitution. And that's the version with like the abstracted thing. I'm just replacing I/O with the type class, but again, not very important. Okay, so this is how you kind of wrap it. And again, if you have a JDBC connection or whatever else, same recipe. You don't have to think. Wrap every method in I/O is going to be pure. But how do you go about using it? So this is actually where things get interesting, and why I think your code changes for the better if you use this approach. So first of all, I have a little trivia. I have a counter. I'm creating this ref. It's a ref of integer, initialized to 0. And again, the type is I/O of ref of I/O of a. So a program that will create this reference. And then I have, again, a for comprehension. Says, well, take the counter, flood map to get to the ref, and update by adding 1 to the counter. And then I'm going to do, again, reference the counter and do get. And then imagine that this is your old program, and it's your last instruction. In main, you just run it. So this is generally like the final bit of your program. So how many people think that this is going to return 1, this program? It's not a trick question. You can, yeah? Other answers? How many people think that this is not going to return 1? Okay, it's one person. Okay, so the good news is that I've already given you all the tools to understand what this does, because as I've told you, the main point of this is that we can apply the substitution model. So I think a lot of people think this is going to return 1, and because they're used to side effects. So they see counter, it has to be the same thing. That's how side effects work. But let's try and apply the substitution model to it. So I have counter there. I'm just going to replace counter with its definition, just like I replaced x with 1 in the very first slide of the talk. And when you do it, you realize that the first line is going to create the ref and then update it. And the second line is going to create another ref and then get the thing from it. So actually, this thing is going to return 0, because these two things create two separate refs. So this is one of the most asked questions in all the channels of the libraries I maintain. Like, okay, how the hell do I make it work then? And I get crazy, like, oh, I should memorize the I/O and all sorts of crazy tries. But actually, it's really, really easy to make this work. Same thing, I have a counter, but this time, instead of referencing counter, I'm just going to pass in the ref. So bear in mind, I'm not passing an I/O of ref, I'm passing a ref as an argument. And now I know that every time I call C, it's the same ref, right? It's just a piece of data. And then, because I want to create it once, I call the creating program once, I flood map it, that's the ref, and I pass it in. And now, this is going to get shared. And again, if you want to know why this is shared, you can just replace, and you're going to see that it's going to be created once and passed twice. And actually, yeah, I've actually done it in the slide. Good. So again, all I've done is apply substitution model, take a name and replace the definition of that name, everywhere I see the name. And then you see that it's creating the ref once, passing it as an argument in both places, and that's it. Okay, so this is the how, that's how you do it. Okay, but why did we introduce this sort of kind of indirection? Is it actually giving us any benefits? I think for most people, they think that the second program is correct and the first program is buggy, right? But actually, they're both very useful because sometimes we want to share some state and sometimes we want to isolate some state. For example, let's say I have a cache. Imagine that the cache is implemented in terms of ref or any other cat effect primitive. And I have two programs that take the cache. Imagine it's a cache of users, so you might do some login and caching their credentials or whatever. Now, in some scenarios, you want these two different programs to have separate caches because you might want to use it for different purposes in the two programs. So the way you do that, you say, well, create cache and pass it to program 1, and then create another cache and pass it to program 2. And now your two features have separate caches. But in other scenarios, you want the cache to be shared because maybe P1 is the one that is putting things in the cache and P2 is getting things from the cache. And so the way you do that, you just say, well, create the cache once and then take the reference and pass it to both programs. And note, and this is how it works basically. So what you're doing, you're basically creating a region of sharing just by passing arguments. Every time you're passing arguments, you're kind of creating these regions where the state can potentially be shared. And every time you flat map, you're basically sealing that region and say, well, in that region, that's where I'm getting a single thing. And then the higher you go in your call graph, the wider the region is. So if you compare this thing here, you have cache and cache. And if you look at the program just below, I just put cache a level above and then passing the argument in both programs. So if you keep going higher and higher and higher, at some point you will create it in main, and that's the equivalent of truly global state. Like your whole application shares the same thing. But with this thing, I actually managed to control exactly what is shared and what is not shared just by passing arguments. So very, very simple technique. Compare it with like singletons or any other crazy approach to doing the same thing. So this is the most important slide on the talk. So the key property is that the regions of state sharing are the same as your call graph. Just look at where the arguments are passed, that's where the state is shared or isolated, and they're both great properties. So we have moved a dynamic behavior of which shares what into a very dumb, simple syntactical property. Which argument is passed to where? We get something that is always understandable by substitution. Doesn't matter how complicated your access patterns are, you can always replace it everywhere and get a simple program that tells you everything you need to know. And we avoid spaghetti by controlling sharing and isolation because we want both, depending on our needs. And we do this just by passing arguments, so nothing fancy. And finally, this is testable by default because to share state, I have to inject it. And because I have to inject it, I can actually inject a mock implementation of that state, like a mock ref or a mock cache or whatever. So you get lots of benefits, even if you don't care about functional programming at all, for theoretical reasons, whatever, you don't care about monads and fancy names. This is like real stuff. This is stuff that we have to deal with every day, how to share state, how to control the sharing, how to test stateful things. Okay, so I want to talk very briefly about this. This is just a technique for abstraction, where we abstracting over a type parameter. And actually, we've already seen an example. It's ref itself. So instead of passing this object, I'm just saying, well, I represent the API of this object like this. We like to call these algebras because like they're nice and composable, but whatever. And every method returns a little program. So it looks like a Java style interface, but it's very different because a Java interface here will return unit. And that's not a program. It doesn't respect that property of substitution, so you can't compose it with other things to build bigger programs. It's just a thing. Once you run it, you've lost your property. So there's a key difference there. And then, instead of using these refs and other primitives directly, what I like to do is I like to build business logic related abstractions that then call these things. So if I want to have a counter, I don't want to deal with ref itself, I want to deal with a counter abstraction. So for example, the way I will model a counter, I can increment, I can get, and I can reset. And by the way, another interesting thing is that I actually like to do this before implementing it. I start with my semantic domain, because I can make it as nice as I want. I can solve any problem, because I'm just making things up. Then I implement the calling code, and now everything is works and is testable. And then I go and implement it. So what happens is that you build in these layers of little languages, each one like simpler than the other, until you've decomposed your program and your problem in chunks that you can deal with. So kind of this multiplies your skill as a programmer, because at some point, no matter how good you are, you're going to end up with a problem that is too hard to tackle at once. And this gives you a nice little technique for dealing with this complexity. And then the way I implement this, again, the shape that we talked about, f for counter of f, because counter is stateful. It contains obviously the state of the counter. I'm going to create a ref. It's a program that returns a ref, so a map to transform the result, which is the ref. And I can create this abstraction. And the implementation is just trivial. Increment is just update on the ref, and then I can get and I can set to 0. And I can use this thing to build programs. So for example, this is a thing that increments the counter once a second. So he has two abstractions. One is timer, which is from cat's effect. The other one is this counter, which I've just built, and returns this IO. And what it does is lives for 1 second, increments the counter, and then recur. So just increment it for 1 second. Another small interesting thing is that this leaf is actually not blocking a thread. It's non-blocking. So you can have a million of these leaf only on like 2 or 3 threads or even 1. And I have a talk on fibers that explains how this works under the hood, but it's a bit more kind of complex. But you don't have to think about it. It's just non-blocking. You can run on many, like 100,000, a million of these without blocking threads. And actually, when you start exploring the ecosystem, it's full of this. So you learn this pattern once, this simple pattern, which is, funny enough, so simple to understand once you've seen it and so hard to figure out by yourself, this just passing arguments. It's everywhere. So cat's effect, ref, defer, semaphore, and var, they all have this. We in FS2 have queue, signal, and topic. HTTP4S client returns that, which always confuses a lot of people. Why an HTTP client is stateful, but actually we have a connection pool there. So you can decide which calls need to share the same connection pools and which calls have separate connection pools. Again, just for passing arguments. And then we have a very complex one that translates between FS2 and reactive stream with like crazy state machine. So it's a very, very common abstraction, and you can use it to build your own as well. So, and finally, I've just shown you with I/O, but you can have more. You can have a different type. So another very typical example is with resource. So resource is a type that gives you resource safety, gives you the ability to open something and then to close it. So with ref, you don't need to close it, but imagine a socket. And because we're representing everything as these regions of sharing, I also get a very simple way of saying close. It's just like at the end of the region. And so you're going to see a resource of f of counter or a resource of f of connection. And finally, with stream, FS2 stream, you get not only resource safety, but also a very nice, beautiful model of concurrency where every stream is a lightweight thread that you can compose with other streams and do all sorts of things. So if you're interested more in this aspect of design, I have other talks on stream and ref and defer that tell you how to build like actual caches and concurrent stuff. But to recap, so referential transparency rules. Functional programming is not about avoiding side effects, and it's not about being morally superior to impure code. It's just about this syntactical property. And concurrent state happens in I/O, so the statement is cool. If you have a use case for it, by all means, use it. But if you do server-side code, and I imagine most people kind of do something similar, you have concurrent state, you have to use I/O for that. And also, the key thing is that when you apply the referential transparency to statefulness, the regions of sharing are the same as your call graph. It's a very nice way of controlling isolation and sharing. And finally, build your abstraction on top of these stateful things with Tagless Final. So conclusion, concurrent share state and effects in general are not a weakness of Purify, they're a strength. So common myth is that when you have some simple non-effectful transformation that you can do map and flat map, but then when you need databases and stuff, then you need to go to side effects. I would say it's actually the other way around. If you have a very simple transformation, you can use whiles and bars for performance, like the initial map. That's perfectly fine. But when the hard stuff comes, when you have concurrency and an interruption and resource safety. That's when I want functional programming, because I like to reason about these things compositionally, because they're hard. So that's it. So I'm on Twitter. You can reach on Gitter at System of Omega. And I have all the slides and all the other talks at my blog. And thank you very much for your time.